not surprisingly, talk about more massive stars. So we have looked at the range up to the transition between traditional HEB stars and red supergiant stars. So, Philip, please.
Sure. Can you see my screen? Okay.
Yep.
All right. Well, I'm going to be talking to you about some of the unsolved problems in red supergiants. I want to start off by dedicating this talk to George Wallerstein, who passed away a couple of weeks ago. He was both an amazing astronomer, an amazing human being, and during this conference, I've been struck by how much he would have really enjoyed it and how much he would have contributed to it. So, of course, I was deeply honored when I was invited to give a summary talk. And then I realized it was a lot like being invited to participate in the Konobe-Maru scenario. And the similarity, of course, being that both doing a conference summary and participating in the Kobayashi-Maru scenario is that these are no-win scenarios. There's no way that you can make do justice to everything you've heard. And the only way that anyone has ever found of solving this problem, as you doubtless know, is by changing the conditions of the scenario, i.e. cheating. And fortunately, all of you speakers have made it possible for me to cheat, to make this easy for me. You were asked to not just talk about your most recent paper, but to instead talk about the field as a whole and to delineate what the interesting and important questions are. And that has made it incredibly easy in some ways to do this summary. So we'll see. And I'm going to apologize in advance for mispronouncing everybody's name. As my wife often reminds me, I often mispronounce her name. So please don't take offense. So Erin Farrell opened the meeting by describing the challenges and open questions in modeling red supergiants. Given the luminosity and effective temperatures of these stars, we can infer the core mass, but we can't get the overall mass of the star. We can't tell what's going on in the center either, that it's not a unique enough mapping. And I'd like to do a little sidebar on fundamental parameters of red supergiants, and just remind everyone that while Gaia is great, it's not magical. That the parallaxes we get from Gaia are good out to maybe 500 parsecs, so much better than what we can do from the ground. But I don't know of any red supergiants that are that close, other than perhaps Betelgeuse, that by the time you get to the couple of kiloparsecs distances of galactic red supergiants, the distances are uncertain. We heard from Marcus about the wonderful things we can learn by interferometry, but even so, that's not magical either. In the Milky Way, our distances are uncertain enough so that this dominates the uncertainty in the luminosity up to about 0.3 dex. We can avoid this problem by looking at red supergiants in nearby galaxies like the Magellanic Clouds. And I'll also remind you that while the effective temperature scale is pretty well pinned down, it's not completely certain either. And just as a little reminder, the way you classify red supergiants is from the strength of the titanium oxide bands, and these bands are extremely sensitive to temperature. These are from the MOGS models. And so one way of getting the effective temperatures are by fitting the depths of the titanium oxide bands. But we have known since the very beginning, when we started doing this work, that the MOGS 1D models give differences of a couple of 100 degrees Kelvin between the spectral energy distributions and the depth of the titanium oxide bands. And when Emily Levesque was my summer student and we were doing our first papers on this, what we quickly found was that the broadband photometry and the titanium oxide fitting gave slightly different results. And here's a plot from one of these early papers that show the systematic difference that we get from using V minus K from and a calibration by the MOGS models versus fitting the titanium oxide bands using the MOGS models. And the differences we saw then were about 150 Kelvin. So Why? Is this due to circumstellar dust affecting the spectral energy distribution? We know there's peculiar reddening and or scattering. We can see this in the turn-up on highly reddened stars. Are these deficiencies in the 1D MOX models? Do we need 3D models or WINS to resolve this sort of discrepancy? And a question that I've been curious about is if anyone's tried this using the Phoenix models, do we get the same answers? I made a little Goldilocks set of figures just to sort of illustrate the size of this effect. This is what happens if you place red supergiants and M33 on the HR diagram using J minus K colors using the MOX expected calibration between temperature and J minus K. And you can see that they're a little bit too long. If we subtract 150 degrees to simulate what we would get possibly from fitting the titanium oxide bands, we see maybe they're a little bit too cold. If we were to subtract 100K, a little bit closer. However, I think this doesn't mean anything other than that the differences are slight. Both Aaron and Jared Goldberg's talks reminded us of the importance of the mixing length parameter alpha. I think Madera and Minette in 1997 were the first to really delineate the importance of how far where the Hayashi tracks are depends on what you adopt for alpha. And then this has most recently been discussed by a very nice paper in Monthly Notices by Gonzalez Torres et al. And here is a figure that Aaron showed us from Shan et al. 2018, showing the differences between where the Hayashi limit lies if you use alpha 1.5 versus 2. Jared argued that alpha of 2 to 3 is probably more appropriate based on his 3D modeling. And I dug into the literature a little bit. Geneva uses 1.6 for their high mass stars, BPAS uses 2, and yet there's no difference in where their Hayashi tracks lie. This is from Emily's textbook. I was very curious about this. I emailed Jan Eldridge last night, and she said something I thought that was very enlightening to me, which is the exact implementation of how you include the mixing length matters. And so perhaps this is a little bit more complex than we might think from alpha equals one value versus alpha equals another. I also think it's good to keep some perspective on how well we do know the physical parameters. Although the MOX SEDs and titanium oxide results don't agree perfectly, they agree that within a couple of percent. And this is better than the situation than we know the effective temperature scale for OB stars. And for OB stars, it really matters. If you mess with the temperature, because of the bolometric correction changes by gigantic amounts. While for red supergiants, if you're starting with K, it makes almost no difference in the deduced luminosity. A change of 150 K is equivalent to less than 0.05 dex if you're starting from the K band. And I think it's also good to remember how bad things really were in the olden days. When Knut Olsen and I first got interested in the red supergiant content of the Magellanic Clouds, this was really surprised me when we made an HR diagram and put on evolutionary tracks. If you use the calibration at that time of what the red supergiant temperatures were, they were nowhere near where the evolutionary tracks said they should be. They were far more luminous and far cooler than what the track said. After Emily did her thing when she was my summer student and we recalibrated the effective temperature scale, this is what we got. Much better agreement. And so perhaps one way of looking at this is that things aren't actually so bad. We heard a very nice review talk on determining the metallicity of red supergiants, which allows you to determine their ages at some level. This allows one to probe whether or not there have been multiple generations of star formation in some of these young clusters. The answer seems to be no. To do this, you do have to have faith in these 1D models. And again, I think it is perhaps overdue for a critical comparison of what the MAUX models and what the Phoenix models are telling us. We were also reminded that red supergiants help drive the chemical evolution of galaxies. But what we really want to know is what the time average mass loss rates are for red supergiants. And how can we do this? We're pretty good at determining what the instantaneous rates are. We can go out and we can measure what the thermal emission is from the dust, and we can apply your favorite gas to dust ratio and determine what the mass loss rate is. But there is this tremendous dispersion with luminosities, as Emma Beezer alluded to in her talk. And this is a plot from George Monet's paper in 2015, where we see that at a given luminosity, there's 2 orders of magnitude difference in what the measured mass loss rates are. So Emma did something I thought which was very clever and innovative, which is to remove one of the variables, that by using clusters, you can restrict your observations to red supergiants of one particular mass in the cluster, assuming, of course, the cluster is strictly coeval. And that allows you to then, from looking from one cluster to another cluster, see differences in mass loss rates that are attributed to either metallicity or to what the mass is of the stars you're looking at. But I think we're still faced with a larger problem, which is how to account for the mass that red supergiants lose during their super Eddington phases, and determining what the time average mass loss rates are. Aaron also reminded us during that first talk that there's a way out of this, which is that the red supergiant luminosity functions are very sensitive to the total amount of mass lost during the red supergiant phase. If you have a high mass loss rate, then the star will go back from a red supergiant back over to the blue side more quickly. And so the higher the mass loss rates, the more you will remove stars at the high luminosity end of the luminosity function. So in some ways, this is a solvable problem. If you make a luminosity function, this is from a recent paper where we looked at the luminosity function of a section of the Andromeda Galaxy, M31, and compared this to the projections of the Geneva evolutionary group and the BPAS groups. You will see that there's almost no difference between whether you only deal with BPAS single or BPAS binary models, doesn't matter. But what we do see is that the BPAS models, which adopt the standard de Jager and Reimers relations for mass loss prescription during the red supergiant phase, they overpredict the number of observed red supergiants at high luminosities, while the Geneva tracks are closer. But and I don't think this is a solved problem by any means, but this is we're making progress, and I think that this is a way that we can address this in the future. What actually drives the stellar wind? Well, as Holly Andrews and Marcus reminded us, we actually have no clear understanding of what the answer is to this. The problem is how to levitate the material up to where dust can form. This can be done maybe by pulsations or convective forces. And of course, we have to remember the important role of magnetohydrodynamic alphane waves in the chromosphere. Stan Iwaki and I were corresponding on this issue a few decades ago, and I've quoted his email in several papers. And what he said was, it's really hard to do this with OB stars. The surface gravities in CGS units, the log G is like 4, and you really have to get the material. It's hard to get the stuff up there. But with red supergiants, you're dealing with a glass that's already filled to the brim with water. The surface gravities are 4 orders of magnitude smaller. And so you're basically walking along the room holding this glass that's full of water. And while we don't know the exact mechanism, it seems to me that driving the wind is maybe not that big a problem. Marcus reminded us also of the large variety of formation mechanisms for circumstellar material and dust. Current models, not even 3D, can explain the levitation of molecules. What else do we need? Well, for O-stars, we didn't really solve this problem until we used a quasi-hydrodynamic solution that combined both the photosphere and wind. You can't just take the wind and slap it onto a photosphere. That's not a self-consistent model. But if you do it self-consistently, then I think that this helps address the problem. We were reminded that, we were told actually, that AGBs may all have some sort of companion in order to explain their circumstellar structure. But we know now that this is not true for red supergiants. In Catherine Nugent's talk, she argued that any stellar companion of red supergiant would preferentially be a B-type star, and that the binary fraction is much smaller, 20 to 40%, depending on the metallicity of what's been quoted for OB stars, which is 70%. And she further made the point that Ricardo Dorda and Lee Patrick get the same numbers for the LMC as she does, using a totally different technique, just looking for radial velocity variations. So why are these numbers so different? Why do we have 20 to 40% binary frequency for red supergiants, but 70 or more for OB stars? And I think that she did a nice job of answering that. And I think this is also a good place to stop. Thank you very much. This has been a great conference, and thanks for all these interesting talks, and thanks to our organizers for putting together such a fantastic meeting.